So we are now at the most difficult part of the polynomial unit. This is polynomial division, and this lecture is in fact so dense and filled with material that we need to actually split it into two parts in order to get through everything properly and with enough examples. Okay, so before we start, I just want to remind you of a couple of things from division. Just your regular long division. So just some basic facts. Okay, so let's say I wanted to divide 317 by the number 3. Okay? I don't know off the top of my head what that is, but there are a couple of ways you could go about it. You could use a calculator, which is all fair and well, but the problem is the calculator, if you do want a calculator, I'll do it right now. The problem is you usually get like something like this, 105.6. Okay? And that's sometimes a little hard to interpret, right? Depending on how messy this number and this number are. So another way you could do it is by doing long division, and this is what you learn in elementary school. You learn how to long divide. And how did you divide these? Well, all you have to do is see how many times is 3 going to 3. It goes one time, and then you do this whole process, and you get 105, and you get a remainder. You get a remainder 2. I'm not going to do it right here. But essentially, this is the type of division that we are interested in here for our polynomials. Okay, we are going to be doing this type of division with remainder. Okay, so let's just maybe think about what this whole thing means. Okay, I did 317. I know, right? It's a new color. 317 divided by 3. Okay. And what did that give me? That gave me 105. This new color is underwhelming. Remainder 2. I might have to switch back. I think I'm gonna rewrite that, yeah. 317 divided by 3 is equal to 105 with a remainder of 2. Okay? What does that really mean? Okay, well that means that I can rewrite 317 as a multiple of 3 times 105, but then I have to add 2 in order to get back 317. And you can check that 3 times 105 just gives you 315, and you add the 2 to give you 317 back. Okay? Now each of these things, they have specific names. Okay? And I always forget the names, which is why I'm going to remind you what each of these things are called in the division operation. So the anatomy of our division is going to look like this. This thing over here is called the dividend. Okay, that is a horrible color. Oh my god, this is sad. This is a sad moment. This is the dividend, okay? This thing here, the result of our division, is called the quotient, okay? And because orange was failing its job miserably, I'm gonna have to try and use green. Oh, that's a lot better. This is the divisor, and this is the remainder. Okay, make sure you take this down. Look, the terminology is not super important to me, but there will be times when I will make reference to them, and I have gotten on previous tests on this unit questions literally about the terminology that I completely bombed because I never paid attention to it. So you might be comfortable with the idea, but just take note of the terms so that you don't fall into the same trap. Okay? Although I will say out front, I'm never going to ask you or quiz you on any of these terms. It's just terminology that you should be comfortable with using in the future. Okay, so this is the anatomy of our division. Okay, so what does this have anything to do with polynomials? Well, it has everything to do with polynomials. So with polynomials, we can do the exact same thing. Let p of x, so let p of x be a polynomial, which means p of x is a function of the form a n to the xn. I'm not going to write the rest of it today. 0. Okay. So that's how p of x looks like. And our idea is to try and divide the polynomial. Why do we want to divide the polynomial? Well, because the only way to get your polynomial in factored form is to divide it, unfortunately. And it's a messy process. A lot of people get confused by it, and it takes a while to learn. In fact, the only way that I can really solidly teach you how to divide polynomials is just by doing a lot of examples, and hope that you can catch on and follow the pattern. There's unfortunately no really good way to do this because the act of division itself is very complicated. You may not realize it right now, but whenever you're dividing, you're actually doing something completely unrelated to what you believe division is. Okay? So right now you probably believe that when I'm doing 317 divided by 3, I'm taking, for example, 317 cakes and dividing them between 3 friends. That's not what's happening. There's something much, much deeper that's going on. And unfortunately, you need a lot more advanced math to be able to fully understand and appreciate division for all of its beauty. Okay? So ignoring that now, let's think about what it means to divide a polynomial. And we're not just going to divide a polynomial by a number. That's kind of a stupid thing to do. We want to divide it by other polynomials. And in this case, I'm actually interested in dividing my polynomial by linear factors. What is a linear factor? I'm going to write the definition up top. So maybe I'll erase this. And I'll keep this up here, the schematic, just so that we have some analogy to go off of later. But a linear factor is one of the form ax minus b. Okay? More often than not, a is usually 1. Okay? So, let's just pretend then that a is 1. So for now, we'll just pretend we have x minus b. Okay? And what we're going to do is p of x divide by x minus b. Now maybe you can come up with some clever examples in your head that will make this really easy. For example, let p of x, here's a quick example. If p of x is equal to x squared minus 4, and our linear factor is x minus 2, and we want to divide by x minus 2, then p of x divided by x minus 2 is quite simply x plus 2 by difference of squares. Right? This is a lot of what we did in the first unit. However, it will often be the case that you don't get something as nice as this. Okay? In fact, if this was like a 3, for example, you'd have no clue what to do. Which is why we need a more solid concept of division, one that is reminiscent of this. And the amazing thing about polynomials is that you can actually do the exact same thing as you did with regular numbers. You can do a sort of division that gives you the following: a divisor, a quotient, and a remainder. Okay? Okay, so let me dissect this for you. So what we can do is we can pretend that x minus b is our divisor. So we can actually rewrite our polynomial p of x as a divisor. I'll do it in green. And our divisor would be this x minus, this linear term, x minus b. Okay? And then we would get a quotient. We would actually get a quotient. So, but our quotient, as you can see here, it won't look like a single number anymore. It will be itself a polynomial. So we'll call this other polynomial q of x for the quotient. Okay? And the only thing that might be a little strange now is that you might have a remainder, right? And the remainder, unfortunately, is pretty messy. It also might be itself a polynomial. So I'll do it in orange, even though I hate orange, r of x. Okay? Now this is a very, very bad thing. We have no clue how to dissect something of this scale. And, you know, the first person who might have done this might have looked at this and given up. But, you know, somewhere along the line, someone must have realized, hey, there has to be a way to do this. So they thought about it really hard, and then they noticed something really weird. Okay? Here's the really weird thing that they noticed. They thought, well, hold on a second. Over here we have a bunch of things with x, and over here we have something with x. Remember, x is just a variable, right? I can put in for x whatever number I want. So, I don't know, why don't I just put in like b? Why don't I put in b for x? And that might seem like a very strange thing to do, but look what happens after you do that. P of b is equal to b minus b times q of b plus r of b, because you have to substitute in b for everything, right? But b minus b is 0, and 0 times something is just 0. So this whole thing is going to disappear, and you're left with p of b is equal to r of b. Well, that's very strange. Okay, well, here's the thing. In cases like this, like the one up top here, what is r? What is r? R is actually 0, right? So, in order to dissect that above example, we have our polynomial p of x, right? And our divisor is x minus 2. Our quotient, remember, was x plus 2 because that was the result of our division. But our remainder was 0. Okay? So what does that mean? What does that mean? Well, suppose r of b is equal to 0. So let me just write that here. Suppose, actually, let's get rid of this because I think I've made pretty clear now what this whole thing is. So suppose that r of b is equal to 0, or just in general, r is equal to 0. Suppose r of x equals 0. In other words, it doesn't exist, like in our example up here. Well, then something incredible happens, because then we get p of b equals 0. Remember what we were trying to do here? We were trying to find roots of our polynomial. And by definition, a root is a point on the polynomial where if I evaluate the polynomial at that point, it gives me 0. Graphically, again, it's just when the polynomial intersects the x-axis. All of these points satisfy this condition. P of b is equal to 0, where like this is b, for example. Okay? So this is extraordinary. This is absolutely extraordinary because what this is saying is that if I plug in b into my polynomial and the result is 0, that tells me two things. Firstly, okay, so let's erase this. So suppose now that p of b is equal to 0. That implies two things. Okay, the first really important thing, is that r of x and r of b, but really all we need is r of x. R of x is equal to 0. R of x doesn't exist. It's like this, right? We get a case where r of x is not even present. Okay. The second thing that it implies, and this is by far the more important thing, p of x divided by x minus b, right, is equal to some polynomial q of x with no remainder. Okay? Now, why do we care so much about this division? Well, it's just like how when you divide numbers, if you keep dividing things, you'll be able to tell all the factors of your number. So, where can I do this now? Let's do this, I'll erase some stuff on the top. So let's take a number like 36. Okay? If I take the number 36, right? The first thing I can do, for example, is divide it by 3. If I divide 36 by 3, then that gives me what? 36 over 3, which is equal to 12. Okay? And then, so, yeah, okay. What is 12? Well, 12 is 6 times 2, right? So 12 is equal to 6 times 2. So that means that if I divide by 2, I'm going to get 6. And if I divide 2 by, let's say, 2 again, I'll get 3. Okay? And then all I have to do to recover my 36 is multiply all these numbers, the 3, the 2, and the 2, and the 3, right? So if I multiply all these together, I'll get back the 36. In the same way here, right? Sorry, that might have been a bit confusing, but anyways, in the same way, you basically have the exact same thing here. So if I keep dividing by these linear factors, eventually the hope is that I will get my polynomial p of x. So eventually, oh, now the orange decides to show up. Eventually p of x will be factored. You do have to keep track of all the factors, but eventually you will get there. Let me just make sure it shows up at all. It's decent. It's decent. Okay, so eventually p of x will be factored. That is the whole point of this. Okay? So, what we have just uncovered here, and what is stated right here, it has a special name. And that name is the remainder theorem. Okay? So, remainder theorem. Okay? So, let me just maybe rewrite it in more clearer terms to explain what we've uncovered here. Let x minus b be a linear factor, and p of x a polynomial. Then we have p of b is equal to the remainder of the division p of x divided by x minus b. Okay? Because remember, when we divided by x minus b, all we had was this remainder term here. Okay? Sorry, sorry, I'm losing it. When we divided first, and then substituted in b, we got, once again, the remainder. Okay? That's all there is to it. Okay? I'm just thinking now, did I miss anything? No, I think we're okay. Yeah, we should be okay. Alright, so hopefully that didn't lose you too much. We are going to apply this in the next couple of lectures, so don't worry, we're going to see this plenty. So if you didn't get it now, there's plenty of opportunities to get it afterward. The next thing that we need to do is figure out how we are going to divide. So we have some knowledge now, right? If we want our remainder to be equal to 0, all we have to do is find values b such that p of b is equal to 0. I want to maybe make this clearer just by giving you an example of this. So I'll use the example that we had earlier up on the board, which was x squared minus 4. Right? And what did we do? We tried dividing by x minus 2. Okay? And what did that give us? Again, it was x plus 2 with no remainder, right? So there's another way we could have gone about this. There's another way we could have figured out x minus 2 is the right thing to divide by. Okay? And here's how. We use our remainder theorem. So what you notice is that if you put in a 2 into p of x, p of 2 is equal to 2 squared minus 4, which is equal to 0. So that means that p of 2 is equal to 0, and by our remainder theorem, what that means is that p of x divided by x minus 2 has no remainder. So I hope you copied down the remainder theorem, because if you did, you would see that this is exactly what this implies. So this tells us right off the bat that it is possible to divide p of x by x minus 2. Now this one was easy, right? This is a difference of squares. You didn't have to use any of this. You could have just used difference of squares. Let me show you an example where you can't use difference of squares because like you just can't. You don't have the tools to be able to do it. Okay? My example, I wrote it down here. Alright. So my example is x cubed minus x squared minus 8x plus 12. Okay? So what I'm going to do is I'm going to think of values. So question, what values b will give p of b equals 0? Why am I asking this question? Because if we figure that out, that means that p of x divided by x minus b is going to have no remainder. And no remainder is good. Okay? And not only that, but it will also mean that b is a root. Okay, so let's go about doing this. I want you to guess some values. Don't worry, I don't pick like some crazy numbers to put in here. Just try like 1, 2, -1, -2, and you'll eventually find that 2 works. So p of 2 is equal to 0 because 2 cubed minus 2 squared minus 8 times 2 plus 12 is equal to 0. This is 8 minus 4 minus 16 plus 12. All that, if you do it, it's equal to 0. Okay. Maybe you were a little more adventurous and you tried -3. You would have also noticed that p of -3 is equal to 0. Okay? That means that -3 is also a root. Okay? Alright, now we are at the tough part. So we figured out that 2 is a root and maybe -3. The thing is, I don't want you to try 2 numbers. As soon as you come across one number, you can stop. And this is a good thing. You just have to guess a couple of numbers, and usually the numbers are not too hard to guess, but eventually you'll come across one that works because this thing is equal to 0. And then you can do polynomial division. Okay, how do you do polynomial division? This is the big question that we've been leading up to this entire time. I'm going to do polynomial division using that example that I just put up on the board. Okay. So, just to recap, what we've done so far with this polynomial is we've stated it as x cubed minus x squared minus 8x plus 12. Okay? Then we found that p of 2 is equal to 0. What that implies by the remainder theorem, I'll write it as RT, by the remainder theorem, that means that x minus 2 is a divisor of p of x with 0 remainder. And that's a good thing. Great, so now what? Now what we are going to do is divide this polynomial by x minus 2, and we will expect that there is no remainder. Okay? But something interesting should happen after that, hopefully. So here's how you do polynomial division. It looks very similar to the way you did your regular division. So we have x cubed minus x squared minus 8x plus 12. And you ask yourself the question. So here's the point of it. You can't put x into this an infinite amount of times. Okay? As soon as x stops fitting into this, we can't divide anymore. We're gonna get a remainder. Alright? Now, so what we're gonna do is we're gonna see how many times does x go into x cubed. In other words, what number times x, so think, what number times x gives me x cubed? Think about it for yourself. and it's actually x squared. Okay, x squared times x gives me x cubed. So what you do is you put an x squared here, and then you take this top thing and multiply it by this whole thing in the divisor. Okay, so if you do that, you get x cubed minus 2x squared. Okay, because x squared times x is x cubed, x squared times minus 2 is minus 2x squared. Then you do the same thing that you did in old high school long division, elementary school long division, sorry. You subtract the 2, x cubed minus x cubed is 0. Good, it better be 0. You should always get a 0 here. Then minus x squared minus minus 2x squared is equal to x squared. Okay, minus x squared minus minus 2x squared is equal to x squared. Okay. Then we repeat the process. So I want you to think now, what number times x will give me x squared? Okay, because this is the new thing that we have to work with. So if you think about it, it's actually x. So we'll put an x up here. X minus, x times x is x squared. And x times minus 2 is minus 2x. Okay, we have to bring this thing down. I know, this is probably triggering you right now. But yeah, that's the way we have to do it. So minus 8x minus 2x is equal to minus 6x. So we'll put a minus 6x here. Of course, these two cancel out and give you 0. Okay. Lastly, how many times does x go into minus 6x? So again, we ask ourselves the question, what times x gives me minus 6x? So of course, the answer is minus 6x. Minus 6. Because minus 6 times x is minus 6x. Okay. Then we multiply this whole thing again. So minus 6 times x is minus 6x. Minus 6 times minus 2 is plus 12. Remember, we have to bring the 12 down here. And of course, when you subtract these two, they're the same thing, so you get a 0 remainder. Okay, why did I spend all this time doing this? Because here's where the magic happens. What did we just find? We found that p of x, which is some big messy thing, whatever, divided by x minus 2 is equal to x squared plus x minus 6, right? Now, if you're paying attention, you can actually factor this, okay? Think about it for yourself quickly. You can factor this into x plus 3, x minus 2. Now, the magic is this. I just have to multiply both sides by x minus 2. Okay, x minus 2 and x minus 2, you can square that. And wow, look at that. I got my polynomial into a factored form just by doing this division. Okay, so this allowed us, this division thing, allowed us to take care of a cubic. We couldn't factor cubics, general cubics before. And remember at the beginning, I promised that we would go eventually into factoring these kinds of really strange expressions? Well, look, we're doing it right now. Okay, this is how you do it. It's hard. It's really hard. Now, there is one comfort that I can provide to you right now, which is that next lecture we are going to cover a much easier way to do this step. The idea is going to still be the same. We need to find some things to divide the polynomial by in order to get into a factored form. However, this is like the least efficient way to do it. However, this is an important idea and it's going to stay with you for a very long time. It actually expands on your ideas of long division. So I actually want to spend the remainder of this lecture doing polynomial division this way. By the way, this is called long division. Okay. So let's do another example. So this is polynomial long division. Okay. So here's our next example. A little trickier. We're going to divide our polynomial, which is 4x cubed plus x squared minus 2x plus 1. Divide by 2x squared minus 3. Okay? Alright, let's do it. It's hard work, but we're going to get there eventually. So again, 2x squared minus 3 goes here, and 4x cubed plus x squared minus 2x plus 1. So I'm hoping that by the end of this example, you would see the general pattern on how to do it, and I can give you some examples, so you can try some examples from the homework now to be able to just work on this skill. Of course, this is not too difficult to do, because, this is not too difficult to do on your own when you're at home and you have a computer, because there are plenty of things online that you can use to double check your work. So for example, you could go on Symbol Lab, you can do polynomial division very easily. You just type in your polynomials and then ask them to do the division for you. They'll give you the answer, okay? It's not that difficult. But we have to learn how to do it by hand because we don't have Symbol Lab on tests in school, okay? So remember, we're really only looking at the first term here. We don't really care about the minus 3. As soon as the 2x squared cannot fit into this thing anymore, we have to stop. It doesn't matter what the minus 3 does. Okay? Ideally, if we were a computer and we were really good at this, we could see, we could literally see how many times 2x squared minus 3 goes into this thing. But we are not. We are humans, and we don't have a good sense of what 2x squared minus 3 is. Okay? So we have to do it the hard way. Also, not to mention that if we could do it, we wouldn't be doing polynomial long division in the first place. We would just be spitting out the answers. Alright, remember our first question is, what times 2x squared gives me 4x cubed? Because this is the first term, right? So if you think about it, it's 2x. 2x. Ah, the orange is showing up. Great. So we put the 2x here. I like to put it right above the same terms, like these are all the x terms. It's just a way for me to keep organized. Okay. So now what I do is I take this number and I multiply this entire thing by it and I put it in the bottom. 2x times 2x squared is 4x cubed, good. But 2x times minus 3 is minus 6x. Okay? Notice there's nothing in the x squared term. That's okay. There's like a 0 here. So then I do my subtraction. I get 0. X squared minus 2x minus 6x is equal to 4x. So we put a 4x here. Okay? Next up, we see how many times does 2x squared go into x squared. You may be hesitating here. You may be like, oh, it doesn't, right? It's like you're asking like how many times does two things go into one thing? Well, don't worry. We can use fractions, okay? It'll work. So what times 2x squared is equal to x squared? And you think about it, and it's just 1/2. Okay, so it's 1/2. Sorry, I'll do it in orange. I like being consistent. Okay. All right. So then I multiply this whole thing by 1/2. What happens? 1/2 times 2x squared is just x squared. Good. 1/2 times minus 3 is minus 3/2. Minus 3/2. Again, notice there was no x term in here. That's okay. We can imagine there's like a 0 here. We just have to bring down the 1, right? My numbers are all over the place. Okay. Then I do my subtraction. Sorry, the lines are not straight. I'm working on it. So these ones cancel out. 0. 4x minus 0 is 4x. And 1 minus minus 3 over 2 is, let's think about it, it's 2.5, or 5 over 2. Okay? And now we ask, how many times can 2x squared go into this thing? Well, it can't, right? You'd have to multiply by 1 over x. We're not allowed to do that. We only want like whole numbered things, right? Fractions here are okay, but the moment we get into negative powers of x, we've got a problem, okay? So we're going to stop there. And so the result of our division is this. P of x divided by 2x squared minus 3 is just equal to 2x plus 1/2 with remainder 4x plus 5 over 2. So that about covers everything I wanted to say about the long division procedure. Now the only thing that I think is left to talk about here is actually the application of this. So let me just refresh your memory on why we were doing this. We are doing this to get our polynomial in factored form. Now obviously here this has nothing to do with it, right? This is just a general skill of polynomial long division. You should learn to be able to do this properly. However, in the next lecture, we are going to come across a skill that is far more useful for our specific purpose. And remember, our specific purpose was to be able to factor a polynomial in order to graph it. So let me just lay out in the last couple of minutes of the lecture here a sketch of how we are going to do this using division. Okay? The technique that we're going to come across next lecture is just another way of dividing, but it only works when you're dividing with linear factors. And division by linear factors is exactly what we need to do when we are figuring out what our polynomial's factored form is. Okay? So here's how we're going to do this. So first, you're given a polynomial. We'll call it P. Okay? By the remainder theorem, by RT, we need to test values B, we'll call the values B, for which P of B is equal to 0, right? By the remainder theorem, this statement is equivalent to the statement that the remainder, that the division P of x divided by x minus b has no remainder. Okay? So now, what you do is, you perform division. P of x divided by x minus b. Okay? And you will get some quotient. Okay? And here's where you need to make a decision. Okay? Option A. You can factor this. If you can factor the quotient q, then you're done. Because all you have to do is take, all you need to do is take factored form of q of x, and then multiply by x minus b. Okay? Let's say you can't factor it. Let's say you cannot factor it. Then, all you need to do is repeat this process once again. So, you're actually going to go back to here. Except now, your new polynomial is, so repeat using q of x. Okay? Now, you may end up having to go through this cycle once, twice, maybe 3 times if you're really, really unlucky. Okay? But more often than not, I won't throw these like really, really crazy examples at you. Or if I do, I will arm you with the correct tools in order to tackle them. Okay? But you're always looking for ways to factor it, right? So again, a reminder, what I mean by being able to factor is this. So a couple of things should be going on in your head. You can factor a quadratic a lot of the time, or you can also factor a difference of squares, right? Or you can also factor things of the form x plus or minus a squared. Or we'll also learn how to factor difference and sums of cubes. So these are the things that you should be thinking about. If your result, your quotient q, doesn't look like any of these things, then you'll probably have to go back. Okay? All right. There's one last option. There's one last option, and this is like the oddball scenario. Okay? So the odd scenario is that not only can you not factor, but your remaining thing is like you can't actually divide it anymore, right? So what would this look like? Let's see. Actually, maybe I'll do it like this. I think I prefer this better. So let's suppose you can't factor. You actually have to make a decision here. Okay? So your first decision is it an irreducible quadratic? Okay? If it is an irreducible quadratic, then you have to stop. Okay? And if it is a reducible quadratic, then all you have to do is repeat the process again. So else you do this again. Okay? So this is a sort of flow chart of how you get your factored form. Okay? What do I mean by an irreducible quadratic? Well, remember that we have something called a discriminant, right? B squared minus 4ac. All you do is, if you get a quadratic, you use this and make sure that your b squared minus 4ac is either greater than 0, sorry, not the square root. B squared minus 4ac is greater than 0 or equal to 0, right? So let me just put here, it's irreducible if b squared minus 4ac is less than 0. Okay, that's how you check if your quadratic is irreducible. Graphically, all this means is that your quadratic never intersects the x-axis. It looks like that. Okay? Therefore, it will have no roots. You cannot divide it because there will be no number for which p of b will be 0. Okay? Because it never touches the x-axis. That's why you need to stop here. Okay? So, assuming all this, you will get a factored polynomial. So copy this diagram down, pause the video if you have to, and then we're going to move on to how we're going to use this to graph. Okay? So here's the graphing protocol. Graphing. So now what you're doing is you're given a factored form polynomial. P of x, it's the same polynomial. Then all you have to do is A, check degree, turning points, and end behavior. Now, a sub-step of this is to make sure all your factors, ensure all factors are of form ax minus b. And things that you don't want, not b minus ax. Okay, this is what we don't want. We also don't want things of the form b minus x. We also don't want things of the form minus x minus b. Okay? They need to be like this. Okay, where a could be 1. Okay? So, so in this case, you have to pull out the negative signs, just like I showed you last lecture. Okay? From there, all you do is note roots on graph, and then check multiplicities, and sketch the polynomial. Okay? That is your procedure for graphing a polynomial after you're done factoring it. Okay? Learn this well, but you're going to have plenty of opportunities in the homework and in the next lecture to really go through this procedure really, really well. Okay? Now, here is the thing that I was mentioning earlier. I'm just going to briefly mention what we're doing next lecture, which is something called synthetic division. So recall that one of the steps in the procedure was to do division by a linear factor. And a linear factor is of the form ax minus b, right? So we're going to find a tool to do this faster called synthetic division. And the upside to this, the pro, is that it does division with a linear factor really fast. The downside, there was really two, but they're so small that you practically won't care. The downside is that you don't understand what's going on. It's actually quite difficult to explain why it works. You need to be really comfortable with division in order to understand why synthetic division works. The other downside is this. It doesn't work for any other type of factors. So in other words, If you try and do synthetic division without a linear factor, with a factor, for example, like x squared plus 2, it won't work. Like, there's no way to do it. Okay? However, this one pro makes it so useful and powerful that we are going to abuse it when we are graphing polynomials because it's so helpful. Okay, so next lecture, we're going to go through this process of synthetic division. You're going to learn how to do it, and at the end of the lecture, you should be able to go through the entirety of this week's homework. Okay?